Okay, good evening everybody. I hope everyone's having a wonderful day. So before I get started, I just want to mention that assignment 5 is out. Please take a look at the assignment, read it very carefully. In the assignment, I'm getting you to implement an AVL tree. And specifically, this AVL tree, just for the sake of brevity for this assignment, it'll have you implementing a binary search tree that has extra functionality to behave like an AVL tree. But yeah, so a lot of the functions that are on this assignment are those we talked about in class with slight modifications for the most part. But just keep in mind and read all of the specifications very carefully. So anyways, with that being said, why don't we get started, okay? So last day, I was talking about rotations and how we might rebalance the binary search tree, right? Because the one major problem we had with general binary search trees was the fact that we never had this, we could create binary search trees that have very, very poor structure. Their shape leads to it where the height of the tree could be linear in terms of the number of records that are in the dictionary, for example. Which that isn't very nice. I would like to find a way to make it look like a balanced binary search tree. But the thing is, doing this, it might take a lot more work. So what I'm doing is I'm going to maintain that the binary search tree maintains the so-called height balance property. And the other day we proved that maintaining the height balance property ensures that the height of the tree is always big O of log n. So that means that as long as we can ensure that every modification of the tree, whether we do an insertion or a removal, we want to make sure that the height balance property is maintained. This has to be true for all the nodes in the tree, specifically the internal nodes. So that's going to be our goal. So whenever we make a modification to the AVL tree, we want to make sure that we ensure if there's any imbalance, I have a mechanism to do this. And last time we talked about that mechanism. The rotation. The rotation is our best friend. So today I'm going to talk about how we do these insertions and removals, because that's the only time our data structure changes. Otherwise, it just behaves like any old binary search tree. So let's first start talking about insertions. And as we go through this conversation where we try to figure out what's going on, you're going to see that I'm going to reveal more aspects of this operation. The rebalancing operations that are necessary. So let's first start talking about so-called the putAVL. So this is just the put operation for the AVL tree. So here's the idea. First, you just apply put as you had in the binary search tree. Then you just rebalance it if needed. It's really, really simple. So one perk that you get with the insertions with an AVL tree is if you use one of our rotations that we talked about. Remember we talked last day about single rotations and double rotations? We only require most one of these operations. So I'm colloquially referring to a single rotation or a double rotation, the 4 kinds we had last day. Those I'm referring to as rebalancing operations for this lecture. So you might ask, Dan, how is this actually going to play out? So let's take a look. Before I get to the pseudocode, I thought I would just do a tiny example, just so you can get a flavor for what's going on here. So suppose I start off with just an empty binary search tree. So our AVL tree, remember all AVL trees are binary search trees. Just the other way around isn't true. It isn't true that every binary search tree is an AVL tree. So I have my root. And suppose I do a bunch of put operations as per this procedure. So suppose that I do the following. Suppose I first do a put operation where I put a record in of value 1. So call in put. What happens is I find it, and if I hit a leaf, I place the data there at that leaf, and I create 2 new leaf nodes. So if I do a put with 1 as the key for whatever the record is, this is what the result of that tree would look like before I had an empty binary search tree. Now next, if I do a put operation sorry, let me just note this. So I'm going to insert a key with 1, a key with 2, and then a key with 3 and see what happens. So I do it with 2. So I go and I find I have to put it right here because we're just using put. So 2 is going to go right here. I get 2 leaf nodes to create 2 new leaf nodes like this. And then, of course, I do another put operation. Suppose I want to put in key of 3. Actually, before we get to 3, we should maybe make sure that we see what these heights look like. So we know that the heights of all the leaf nodes are 0, right? That's how we instantiated them. Now, every time I put in a new node like this, I need some way of updating the height. So this is something I'm going to bake right into the rebalancing operation that is necessary. So as we add more records into our dictionary, these heights are going to get updated. So far, this is an AVL tree, right? This is perfectly fine. There's nothing bad going on here, right? We're not violating the height balance property at any one node. So somebody's asking if height is a global variable. No, remember, all the nodes have their own heights. So remember, this is a modification we're making for our AVL tree. So now if I put in 3, remember, when I do put, I use get, and I find the node where it should be. And in this case, that means 3 goes right here. I create 2 new leaf nodes. Their heights are 0. And I'm going to update the height as I do this. So we know the height of that is 1. Naturally, the height of this is 2. First thing I want you to notice is that when I put this here, most certainly this subtree, if I just look at this, remember, we know every subtree of an AVL tree has to be AVL, right? So this is indeed an AVL tree. If I look at it to the left, every one of the internal nodes has the height balance property here. I'm going to go up 1. This is indeed an AVL tree, right? Except it's an AVL tree rooted at my node with the key 2 in it. But notice that when I attempt to take a look at this node, I look at its left and its right. Is the node with key 1, is this subtree rooted at this node, as in the entire tree? Is this an AVL tree? No, right? This is why we're going to probably use these rebalancing operations, because you know the height would be, you notice that we're violating the height balance property right here. So that means we have to fix this. So last day we talked about how we do these rotations. So remember I told you about how we detect these. So one thing I want to remind you of is that we had 3 nodes that we usually identified. We had Z, and then we figure out which is the taller of my 2 children. And I had Y, and then I had an X. And if I were to carry through with this example, what kind of rotation should I have to do here? So remember, there's 4 kinds. Remember our 4 kinds? We have LL, we have RR, we have LR, and we have RL, right? Those are our 4 kinds of rotations. Yes, we use the RR rotation, because notice I go right, and then I go right. So if you just look at my nodes identified here, the taller of the 2 children each time, I'm going right twice. That's how you know it's RR. I just read off the direction I'm going. So one thing I do want to mention is that it's typical that you want to try to avoid having to do more rotations than necessary. In particular, if you could do a single rotation as opposed to a double rotation, you do less operations in that way, right? Because it's only really one rotate operation. So one thing I want to point out to you is that very often, if it's unclear which of the 2 taller nodes to pick out of the 2 possible children at Y, you always pick the one on the same side. Usually that's the convention. Why? Because you want to reduce the number of operations you're doing. But from an asymptotic standpoint, it doesn't make any difference. But I just feel like I want to mention this because it'll come up later on in the lecture. So if I do an RR rotation on this, you know I'm just going to apply rotate on Y. So if I do rotate on Y, I'm going to promote Y, and I demote Z. That means Y is going up, Z's coming down. So I promoted Y. I demote Z. So remember, this is Z, this is Y, and that's X. So note that I have the leaf here, leaf here, leaf here, leaf here. Now, you might ask, Dan, how did you do that so quickly? Well, here's the thing that really you'll find very helpful when you're doing these types of rotations. So remember, it is just an RR rotation. So in this case, all I do is do rotate at Y. That's what we described. So if I'm doing a rotate at Y, there's 3 subtrees you have to identify. Namely, this one. Then there is the left subtree. Then this right subtree. So there's 3 of them. You'll notice that this one goes right there. This one gets hang around over there. It just kind of gets exchanged over to Z as its right child. And this one ends up still staying as the right child of 2. So I want you to take notice that when I do a rotate operation, in particular I do a left rotate, I'm doing a left rotation. So what we call a left rotate, so it's a simple operation here. So remember I had this concept of a left rotate versus a right rotate. Think of the hanger I was using the other day. So in this case, I am bringing up Y, but I'm bringing down Z. It means I'm going left. I'm promoting it. So when I go through this process, all I'm doing is applying the rotate operation from the other day. So remember, I promote Y. Remember Miss Kitty? Miss Kitty gets promoted. I get demoted. So what does that mean? Miss Kitty goes up. I go down. Which means that if this is Miss Kitty and that's me, I'm going down. Miss Kitty's going up. And remember, in our diagram I had 3 subtrees, T1, T2, and T3. This is T2, that's T3, and this is T1. Notice that T1, in this case, it doesn't go anywhere. It's still the right child of Y. I want you to take note of that because notice that the heights don't matter in this case. However, some of these might actually change their heights. By demoting one of these, you're actually changing potentially a height here. So for example here, when I made this operation here, notice that X had a height of 1, right? Its height didn't change at all. This is because all I did is I just dragged it along with me, just like the string getting pulled across the hanger. So if we think about this carefully, all that's happening is I'm just doing the rotate operation, the same one we talked about the other day. So I'm just pulling this up. I am just taking these subtrees and I'm just placing them right here. Just as I talked about the other day when I described the rotate operation. So notice that Z, however, because I brought it down, notice now its height has changed. So in this case, I would have to update its height. So notice these are 0. This means Z's height has to be 1 by definition. And then, of course, when I'm done this process, I can always update my height at Y. In this case, now the height is 2. So notice, by doing this operation, I have corrected the issue. But now notice that the root is now Y. So just be very mindful of this. So this is just a sequence of me applying these put operations, but notice that on the third one, I had to do the rotation. So just keep in mind that when you do a rebalancing operation, one of these rotations, you actually only have to do at most 1 when you're doing an insertion. This is because, as notice that I was doing here, I always start with the smallest subtree of any one AVL tree and I work my way up. This is because I always start off at some leaf node when I do the insertion, right? So just keep this in mind. So that's actually the main reason why this is true. Because I always start at whenever there's an imbalance, it happens at the smallest possible subtree. So when I fix it, I'm maintaining the height balance property of that subtree, meaning that the entire tree has to also maintain the height balance property because none of those nodes were affected by this process. Because the only thing that happens is the height of this node either stays the same or it goes down. So just keep that in mind. So there's going to be one weird caveat with this, because I always start at the bottom of the tree. There's a natural question that'll come up later in the lecture. It's like, okay, what happens when I don't have it at the bottom of the tree and it could be somewhere else in the tree? And the question will be, do I have where it's a most one anymore? And the answer is going to be, unfortunately, no. We may have to do several rotations. But if for insertions, it's nice and easy. So that brings me to talking about the pseudocode today. So when I do put, so I start off with putAVL, I just apply put first. So this is the same put I talked about the other day. So this is the put for a binary search tree. And then I determine what node V is. What V is going to end up being the node where the insertion occurred. So for example, when I put 3 in, this is V right here. So that's what V is. So you might ask, Dan, how do I get this node? Now you can either modify the put that I gave you, which tells you either if it failed or succeeded, or you could just simply use the get operation. In the assignment, I believe you're using the get operation. So that being said, there's one last piece here, is this rebalanceAVL. So you'll notice very quickly that the biggest part of this algorithm, which is rather, it looks really short, right? It's really short. That's typical for these AVL tree operations. I've pushed all of the hard work right here. This is the thing that is going to be the fun. It's the actual fun of this. So rebalanceAVL, that's performing our rebalancing operations. So before we get any further, I want to just do a quick analysis of this. So notice so far, I know how to do this and this. I know how to do that if I have an AVL tree in big O of log n time, right? So I know how to do this all in big O of log n. I know how to do all this. The one suspicious case here is this. We haven't yet talked about this. So let's talk about that now, because I have to talk about how we're bringing all of these ideas together to rebalance the tree. There's really two mechanisms I haven't really talked about, to be honest with you. One, how I'm updating these heights. So notice in the example, I walked from this node upward up the tree, updating the heights. Did anybody notice that? I started down here and then I updated its height, and then I updated this one's height, and I worked my way up until there was an imbalance happen. I make the correction, then I updated its height. And I would keep, theoretically speaking, I would keep walking up the tree if there might be more imbalances. So I'm just going to keep walking up the tree, updating the heights. So that's one part of this. The other part of it is how I'm actually doing the rotations. So how I determine those, so I'm just going to take what exactly we talked about the other day, and I'm just going to adapt this all together in one place. So if you're wondering, how does this all come together? It's rebalanceAVL. That's all it is. So let's talk about rebalanceAVL. So this seems to be suppressing a very important detail for our AVL tree, so let's talk about it. So, camera, come on, let's go this way. I'm just about to lose it here. So let's head over here. Now, the one thing you need to know about rebalanceAVL is it has several steps to it. And I've written them in a manner that you should be able to translate into actual code. So here's rebalanceAVL. So the input is going to be a node V where an imbalance may have happened. So I must stress that a rebalance may not have happened. So also I must stress that the height balance property may be perfectly fine. So this one method is in charge of both updating the heights of the tree, but also performing rebalancing wherever necessary. So what this algorithm will do, it doesn't return anything. Instead, it just updates the AVL tree to make it so that it fixes the tree in terms of if there's any imbalances happening. So at the beginning of this, now you might remember from a previous lecture, I told you all about how I told you that there was going to be some mechanism to update the nodes, so in particular the internal nodes. How do I update the internal nodes' heights? It's this line in the pseudocode. That's all that is happening. So if you ever wonder, Dan, how do you know that the height is 1 for an internal node when you put it in? It's this. That's all it is. This is one line. So you might ask, Dan, so what happens after you recompute the height? So remember, recompute height, that's the that was a one-liner pseudocode I gave you the other day, right? So while v is not the root, so I must stress the context of this pseudocode. So when v is not the root, so remember there is a node designated as the root of the tree. The root might change as these rotations are happening. So be very wary of this fact. So the rotations might affect what is designated the root of the tree. So for example, the case I gave over there is actually a perfect example of this. Did you notice how the root of the tree actually changed? It was originally 1 and then it became 2. Did everybody see that? The root actually changed. So you have to make sure when these rotations are occurring, at some point, you're going to have to make sure you update the root of the tree if, for example, just think of Miss Kitty going up and I'm going down. What if I was the root? Then Miss Kitty's now the root of the tree. We're all at mercy of Miss Kitty, okay? So just keep that in mind. So we're just going to be walking our way up the tree. So all this is being done is, so I just take v and I'm going to update it to be the parent of v. So I'm going to traverse my way up following the parents of all of my nodes. I'm going to go ancestor after ancestor, walking my way up the root. And I check the height balance property. So that's the first thing I do. So I look at the subtree rooted at v. So remember, this is not the same as me saying it's the root. I'm saying it's a subtree rooted at v. So remember, that's the node and it's all of its descendants. So I'm asking, is that subtree an AVL tree? So remember, that's all we're doing is that calculation I have way over there on the right. We're just determining the height of my left child and the height of my right child, that they don't differ by more than 1. So remember, this would just be like an absolute value calculation you just simply do. So if it is the case that it validates it's that satisfying that specific condition I have over there, meaning that the heights do in fact differ by more than 1, that means I have an imbalance and I'm going to have to fix it. So I have to fix it. So remember, we talked about this last day. So let y be the tallest child of v. Now you might ask, v, what's a v? So we talked about this in class. Actually, last day, v is actually z in all of our pictures. Do you remember how I had a z, y, and an x? So if you're wondering what v is z in those pictures. So when you look at my remember last time we showed all those rotations and I had z, y, and x? Or z, y, and x, and z, y, and x. What z is v right now. So we're going to determine y. Remember, that's the tallest of my 2 children. So remember, that just simply means I take the larger of the 2 heights. So I pick which one has the larger height as y. And then I take x to be the tallest child of y. So I go down from there and I check which of my 2 children for y is taller. Now, I must stress that if ever there's a tie, pick the child on the same side as y. So what I mean by this is if, for example, say there's an imbalance that happens at v, and say y is on the right of it. What I'm saying is if there's 2 potential children that have the exact same height right here, what I'm saying is pick the one that's always on the same side. So if this is to the right, you pick this one. So pick to the right if there's ever a tie, just like if I have v and if it was on the left. What I'm saying is if there was a tie between their heights, you pick the left one in this case. Just like you'd pick the right one in this case. So this is just simply to ensure, if you're wondering about why we do this or why we can do this, it's simply for the sake of optimization, because think about it. if it has this shape when I do the rotation, is that a single rotation or a double rotation? It's a single rotation. Very good. So it's a single rotation, which, if you remember what a single rotation is, it's just one rotate operation, right? Versus the double rotation, which does two rotate operations. So if you're thinking about this from a performance standpoint, you want to do more single rotations as opposed to double ones if possible. So that's why I am suggesting you, if ever there's a tie, pick the child on the same side. So you just figure out what y is, figure out what x is. Now that you have v, y, and x, you have these three nodes, you know them. You can determine the rebalancing case you're going to apply. So you rebalance subtree rooted at v by performing the appropriate rotation. So when I say this, remember what one of these rotation operations is. So remember, like an LR rotation, or in this case an RR rotation, or an LL rotation. Remember that updates to the heights of nodes are necessary, otherwise we're going to destroy properties that make our AVL tree nice and pretty. One suggestion I can make that makes the implementation of this easier is if you know that, oh yeah, when I do, say, the rotate like I did earlier, when that happens, okay, so it can be that I demote myself and Miss Kitty goes up, right? I promote Miss Kitty. Well, it could also be the case that I get promoted and Miss Kitty gets demoted. So notice that either the left child or the right child of my node might have its height changed, right? But if I'm the one that's getting applied to the rotate operation, I know right away I'm going to be the root of that subtree in a single rotation, or a simple rotation, if to be a bit more precise. But I know my two children have to have their heights possibly updated. So you may as well just do both, assuming that they're internal nodes. So just check that it's an internal node and just update both of them. See, believe me, you'll save yourself a lot of time if you think about it like that. So just cover your butt and just update their heights unless you know exactly which cases to do it. So you apply the appropriate rotation, and then you let v be the root of the resulting subtree. So in this case, if I did a rotate operation, say for example, you notice I rotate on y, you know y is going to end up being the root of that subtree, right? Because I promote y and then I demote v, so you know that you're going to be returning y in this case. Likewise, if a double rotation happens, you apply it to, say for example, I have a double rotation like this, like say it's v, y, and x. You know x is going to end up being the root of this subtree, right? Because it just does two rotate operations. So in this case, you would just return what x is. That's what v is. So I do the rotation, so whatever rotations are necessary in this case. So remember, it's one of the four rotations. So I must stress that when we talk about the single rotation and the double rotation, they're really just two cases. A single rotation or a double rotation. It's just a matter of determining if you're doing LL, RR versus LR or RL. They're just symmetric. So what happens now? After I've done this, regardless if it does happen where the imbalance occurs, I'm going to recompute the height at V, because I'm going to walk my way up the tree, just like I'm taking a strut up the tree. Just imagine Dan walking up the tree to the root, because maybe I'm having a wonderful day and I want to take a walk up to the root of the tree. Maybe there's a friendly owl at the top, which is kind of weird because the root is normally down there. Anyways, so I recompute the height at V, and then I repeat this process. So I repeat now, while V is not the root, I get my next parent, and I repeat this process over and over again. So this is written deliberately in a fashion that we can easily use it for insertions or removals. Plus, it makes sure that our heights are updated appropriately in the tree. So if you're wondering what mechanism is actually updating all of our height attributes in the tree, it's this. This is actually responsible for that. So it's actually serving two purposes. So are there any questions about this pseudocode before we proceed to do a couple of things? One, we have to do the analysis of this, and two, we're going to do some examples where we can actually see how this is done. So if we're doing all good, give me 2 thumbs up. So I'm seeing some thumbs. Okay, good, 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 good. One thing I do want to make a remark about, if you're talking about this from an implementation standpoint, what I would say the 2 trickiest functions to work with are the removals. So for example, we talked about remove for a BST. That one and this one, and anything you do with this is going to be the trickiest part of your implementation of the AVL tree typically in practice. Yes, we did. We talked about recompute height. So I'm confused. Why we made y and x the tallest at the same time? So remember, y is the tallest child of v, then x is the tallest child of y. So remember, there's 3 nodes we're identifying because those 3 nodes are used for our rotation. So just remember, we're identifying these 3 nodes because those are the ones that we had for our rotations. So the purpose of identifying these 3 is to perform either a single rotation or a double rotation, just in the exact way we talked about last day. And all they do, the purpose is to rebalance the tree. So which one is the V again? V is Z in the pictures that we talked about last day. In fact, in that example I did just a moment ago, that's what V is. If you have an imbalance happening, we had 3 nodes, Z, Y, and X. V over there is Z in my picture. So all the examples I did last day, that's what Z is. It's V. So remember, the whole idea here is that if V has an imbalance happening at it, we need to fix that, because otherwise we don't have an AVL tree anymore. Which one? Yeah. So I think I addressed that. So let's do the analysis. If you have any other questions, feel free to leave it in the chat. I'll be happy to try to address them while we're kind of walking through the analysis here. Believe it or not, this analysis is actually not too bad, really, at all. It looks a little daunting, but if you remember everything we talked about in the last couple of lectures, it'll be actually a piece of cake. So first, to recompute the height. It's just some constant number of operations to do this, right? Remember, it's just a single line. I just simply am recomputing the height, and I have those attributes. So I'm just getting their heights, and I add 1 to it, right? Sorry, I get the heights, I take the larger of the 2, and I add 1 to it, right? So it's just some constant number of operations. Inside of here, getting the parent of V, that's a constant number of operations. Checking this height balance property takes a constant number of operations, right? It's just an absolute value calculation. So I'm just simply saying, what's the height of the left child, height of the right child? I subtract the 2. I use the absolute value. So you just simply use the standard absolute value function for doing this. That takes a constant number of operations. Determining the taller of two nodes, constant number of operations, constant number of operations. Rebalancing, remember we talked last day about all of our rotations. All of them take a constant number of operations if I do one of them. Figuring out all of this, constant number of operations. So, recomputing the height again, constant number of operations. So that means that all of the stuff that's happening in here, it's a constant number of operations, right? That's all it is. So, what happens? So what happens when I combine it with the while loop? So remember, when I do an insertion, for example, it's right at it might be potentially the deepest node just above, actually technically it would be just above the deepest node in the tree, wherever V would be when I start this up. So what can this be? How many, what's the relationship for the number of iterations for this loop? Anybody have any ideas? So remember, just like I kind of did that in my example, I started, yeah, so it seems to relate to the height. Yes, very good. So you know it's something like C2 times the height, right? Because I'm always 1 above wherever the leaves are. So, you know, when I take this together, I get C2 times the height. But we know that the height is big O of log n, right? So let's just put this all together then. So I have, so notice that so let's figure out what the worst case time complexity is here. So remember, the worst case is that it's at it's just above one of the deepest nodes in the tree. It's an internal node where one of its leaves is the deepest node. So, with that being said, as h is big O of log n, the worst case time complexity is, okay, well, we have C1 plus C2 times H, right? Well, H is big O of log n, right? So you have a constant plus some other constant times log. Some constant times log, right? So that means that our rebalanceAVL actually takes big O of log n. So there's really kind of two phases if you actually think about the algorithm I just presented to you. There's this down phase where I go down the tree and I do my insertion. And then there's this up phase. And that's what rebalanceAVL does, is it works its way back up the tree following the parents all the way up to the root. So it makes a lot of sense that it would be that when I work my way down, then I work my way up, because my rotations, each one takes some constant number of operations. I most certainly can bound the number of operations as some logarithmic function like I have. So are there any questions about the analysis I did here? So remember, the big idea here is that the rotation takes a constant number of operations. Remember, all the rotation is, what rotate at a given node is just a bunch of pointer adjustments. So it's a bunch of pointer adjustments. So I do a bunch of pointer adjustments, and the only thing I'm suggesting beyond that is you'd have to update their heights. Just like when I seen that example over there earlier, you notice I had to update at least one node's height in case it was one of the two children in that case. So are there any other questions about rebalanceAVL before we kind of get juicy and start playing around with some examples here? Okay, so we're going to see how this process plays out, but I want to complete one picture, well, one thing that I left out here before we proceed, is namely what I have written right here. So remember we said we kind of left this blank, right? So let's fill that in. Let's fill that in. So we know rebalanceAVL now takes... No! So we know that rebalanceAVL takes big O of log n because I just call it once. That means that the time complexity, can somebody tell me what's the worst case time complexity of putAVL then? It's big O of log n. Very good. Very good. Wonderful. So now we know how to perform insertions into the AVL tree in big O of log n. Wonderful, right? And here's the cool part. Here's the cool part. Let's keep going this way. Come join the party. Now here's the cool part about this. I don't like using the word cool because I don't have my cool shades, at least with me today. But I'm not even kidding, I do have shades that they make me look cool. We'll just leave it at that. Anyways, the neat thing about this is that all I now know, so now I know how to perform an insertion such that before the insertion occurs, I have an AVL tree, and now after the insertion, I have an AVL tree. So that's the big thing that we've done here and accomplished. So The one thing that will be remaining after this is figuring out the removals. So I thought before that we should do some examples seeing this process. So we did a much more basic example earlier. Let's do something a little bit more involved. I've just lost my little turtle friend. We might lose my little turtle friend a little bit. Seeing those rotations, it was just like, I'm getting out of here. I'm just joking. I'm just joking. Seriously, though, that turtle really needs to have a nap. The poor turtle just hangs out there all day, just staring blankly into the void of fun. So, let's do an example. So here, I'm just going to create a binary search tree. My apologies. Sorry, I shouldn't have mocked my turtle friend here. We have to be nice to our friends. So, anyways, I'm going to be showing you all the heights. 2, 1, and 3. And the last one here I'll put as 30. So I have 12, 11, 17. Leaf, leaf, leaf. 30, leaf, leaf. If I read it from a level order standpoint. Yeah, I like that one much more for explanation. The turtle's afraid you'll rotate him. Listen, that would be horrifying to myself as well. Anyways. So, question, is this an AVL tree? Just before I get further ahead? Yes, this is in fact an AVL tree. We're okay. Just want to make sure I ask you about these things. It's very important that you can identify an AVL tree. So what I'm going to do is I'm going to insert a record with key 40, and I'm going to update the heights appropriately. So when I do this, when I place 40 in, remember, the whole idea here is that I go right. Remember, I use get first, right? And then I just put the insertion. If I don't run into a duplicate, right? I just simply go where the node should be, and then I perform the insertion right there. So in this case, 40 would be right here. So if I make that modification right here, I'll put 40 right here. The height of these two is 0, and technically the height at this node is 0 at this time. I haven't updated its height quite yet. So we're going to do the insertion of 40, and we're going to go through. So first I did the down process. So I've gone down the tree to perform the insertion. Now I got to go up, right? I got to go up. So I now need to go up. To make this easier to see, I'm going to draw the arrows as I'm going up. So when I do this, I'm going to start right here. Remember, this is the node where the insertion happened. The first thing I do is I recompute the height at that node. And that's when I know the height is 1. And now notice that I look at my two children. They're both leaves. Their heights are 0. So I'm okay. I don't have to do any rebalancing. And then I proceed up the tree. So keep in mind that there'll be an extra recompute that's going to happen shortly after this. So then I go up. So I'm going up to my parent in my next iteration of this while loop. I check if the height balance property is satisfied. Are we okay here? Is there any violation of the height balance property at the node with 30? Yeah, there's no violation here. We're okay. So here I recompute the height. Keep in mind there's nothing that is interesting that's going on here, except I have to recompute the height here. In this case, it's 2. And now I'm going to go to the next iteration of the while loop. I go up to my parent. And now I compare my children. The height is 0 here and the height here is 2. Are we in trouble here? Are we in trouble? Yes, we're in a lot of trouble. See, the turtle is just trying to warning us of the situation. So, a question. We know that the imbalance happens here. So, at this time, we're considering V. Remember, V is presently right here. I get the taller of my 2 children. In this case, it's on the right. So that's Y. And then I get the taller of its 2 children. In this case, it is the one with 40. So question, what kind of rotation should I be doing here? What kind of rotation? Yeah, we do RR, perfect. Perfect, we do an RR rotation. So we're gonna do the RR rotation. And just to make this easier for me, I'm going to draw you a new picture with the RR rotation in place. So remember, an RR rotation in this case will rotate at Y. So when you think about this, remember, you want to identify the 3 subtrees. If you can remember where these 3 subtrees are, you can knock out any rotate operation. So remember, there's always the one to the left of the parent of the node I want to promote. There is the left child of the current node. And then there's this third one, which is the right child. Sorry, it's the right subtree of my current node. So as long as you can always identify these 3, rotate is a piece of cake. So I need to do rotate at Y. So what I'm going to do is I'm going to promote Y, and it brings down V. So note that I'll still have 12 right here. I'll have 11 here. This isn't affected yet at all because we haven't gone that far up the tree yet. So I'm going to promote 30. I'm going to demote 17. So I know 30 is going to go right here. 17's coming down. T1 is going to go right here. T2 is going to go to its right. Remember, I give it over to my other subtree on the opposing side, whatever T2 is. And then I have T3, which is my right child. So in this case, it's just 40. Now, regardless of which situation I'm currently looking at, I can always update the heights of both of these if I'd like to. So in this case, I have 1 and 1. But remember, from the perspective of X doesn't change where its position is in the tree, right? It's still on the right of Y. So take note of that. It's rather interesting. So just like if I were doing a LL rotation, if it was the case I had the left child over here on the same side, on the opposing side, its spot wouldn't change in the tree. It's just that everything around its parent would be affected. So that being said, now that I've done this rebalancing operation, what V becomes is the root of that subtree. And then I compute its height. So in this case, the height is 2. Remember, I have all of these. That was a 1 before. And now I'm going to walk up the tree again. I'm going to continue my journey up to the root. And remember, the root still had a height of 3 at this time. And I get up there. And then I check the height balance property. And you see, hey, look, just as you would expect, because I told you at most 1 rotation occurs, because we always rebalance at the smallest possible subtree. We're okay. We're done, right? So I've successfully inserted my new record with key 40 into the tree. Are there any questions about what I did here in this example? I must stress I'm going to do another example as well, just so that you can see this. So we always rotate from the parent of the current node. So keep in mind, V is the one that has the imbalance at it. And we determine how the rotation occurs based on this pattern. So in an RR rotation, what happens is you go rotate on Y. But as we're going to see in our next example, we're going to have a double rotation that's going to happen. In double rotations, we do 2 rotate operations on whatever we decide is X. So just keep in mind, single rotations and double rotations perform rotate at two different nodes. In a single rotation, we do rotate at Y. And if we do double rotation, we do double rotation at X. So X in my picture, you would have it at X if it was a double rotation. But this is just a single rotation. So how do we decide which one? Remember, Y is determined by the taller of the 2 children, just like I said earlier. Yeah, 7 was the one that had the imbalance at it, right? Remember our definition. There's an imbalance that happens here because the height balance property guarantees that every one of the nodes should have it where its left child subtree and its right child subtree have to have their heights be no different than more than 1. But in this case, it was not true. It was 0 and 2. That's differing by more than 1. So that means we had to do the correction. So notice there's this down process, then there's this up process. So all the rebalanceAVL is doing this up process, updating the heights of the tree. So this is the mechanism that's actually computing all these heights other than the ones at the leaf nodes, if you're curious, just like I said earlier. Anyways, let's do another example. So let's try inserting 19 into this tree. So we're going to try inserting 19. So remember, when I do this process, I need to find where 19 should be, right? I go right, I go left, then I go right. I find the node where 19 should be, right? So that's right here. I create the 2 leaf nodes for it. Now remember that these are children of this node, but remember, this is the parent of these 2 leaf nodes. So remember that when you're implementing this, that you got to look at it from the perspective of both the children and the parents. We have to be very considerate of the nodes. So these have height 0. And then what I do is I need to do now this up process, the rebalanceAVL process. So let's start over. V starts right here. Remember, that's the node where we should be doing the insertion. I recompute its height to be 1, and I start walking up the tree. So 0 versus 1, we're okay here, right? So I'm gonna recompute its height to 2. I walk up the tree. I have 2 versus 1. Are we okay here? At this node, are we okay at this node here? Is there any imbalance that's happening? Yeah, we're okay here. Yeah, we're okay here, exactly. So I'm just going to recompute its height. So now I'm just going to walk up towards the root here. And now let's take a look at what's happening here. So I have 1 versus 3 for the heights. Are we okay at the root, though? No, right? So let's take a look and see what happens. So remember, this is where V is currently. I look at the taller of my 2 children. This means this one is Y, because its height is 3 versus 1. 3 wins. The taller of my 2 children here. 2 versus 1, I take 2. So now you see I have V, Y, and X. These identify the 3 nodes for my rotation. And what kind of rotation are we using? Yeah, RL, exactly. You go right, so notice it's to the right, Y is to the right of V, X is to the left of Y. So remember, X is just simply the taller of the 2 children of Y. That's all it is. So I'm just computing whatever's the taller of the 2 children just at Y. Just like in this first step here, where I just did this. So we know we do an RL rotation. So just a reminder, remember this is a double rotation. So we're going to do rotate at X, and then rotate at X again. So as long as you remember those 2 subtrees, sorry, the 3 subtrees for the rotate operations, it's fairly easy to carry this out. But you have to have an intuition for how these double rotations play out. I like to think of it like, just like when I talked about, remember my hanger where I was pulling the strings? The double rotation's very intuitive if you actually think about it like this. So think about it. I first rotate X, so I have to promote X and demote Y. So Y is coming down, X is going up. So it means I'm going to be pushing Y down along with its right subtree, and I'm going to be bringing up X. So I'm first going to drag that down, then one side of the tree is going to be borrowing apart from the other. And then after that, I'm going to do the rotate at X again, which will it'll pull up X to where V is. And V is going to be pulled down. I like to think of it like you're tugging these and pulling them up and down, and you're just adjusting a couple of weights. So let's talk about it. So I'll show you what the first rotate does, then I'll draw what the second one is. So remember, I'm doing rotate at X. So I have 3 subtrees that are of interest here. I have this one, I have T1, T2, and T3, right? As long as you can clearly identify these 3, it's a piece of cake. Now, when you're implementing this, remember that this is the left child of X. This is the right child of X. So if you modify what the parent or child is between this relationship here, it modifies what the links are that connects the rest of the subtree to this node. So be very mindful of this. So if you thought about manipulating a linked list as something that's rather complicated, and I like to think of it like you have to require surgical exact measuring when it comes to how precise you are with the manipulations. This, if that is surgery, this is brain surgery. So we have to be very careful. So that's why I'm helping you identify the subtrees. So if I did rotate X, I just want to show you one of them, and I'll draw out the second one. I'll let you think about it. So when I do the first one, it's going to promote up X. It brings down Y. So you're going to have all the rest of this tree that goes up this way. I'm just focusing in on what we have currently going on right here. So we know X is definitely coming up. It's going to be the root of this subtree. It means 30 comes down. So I demote 30. Think of me getting demoted and Miss Kitty getting promoted. This is the first subtree, right? The second subtree, well, this is the second one, right? That's the one I give over to the right subtree. That's 19. And then I have the right subtree, which is just 40. So, anyways, you would update these appropriately. And then, of course, you can, figure out what the height is as you're doing this process. But the point is that you do a first rotation, then you have to do a second one. So there's one more rotate that's going to happen because this is a double rotation. So I must stress that when you get a little bit of practice with these rotations, you should be able to get an intuition around how this works even without having to do it every single step. Which one will go up and which one remains the same? That's because of the definition of the rotate operation. So just remember, rotate X was defined a while back. So we talked actually about this. So we told you the exact operation of this. So that's all that's happening is I'm just using the rotate operation that we described and defined the other day. So do you remember so just to kind of give you an idea. So remember, if I had X right here, when I do rotate on X again, there's going to be V up here. So that's 12 here. You're going to have potentially a left subtree. That was what we call T1. We have the middle one. That's T2. Then we have all of these right here. This is T3. This is exactly what I was referring to when I defined the rotate operation. So when it comes to the heights, let's see. I'm so confused. How do we know which will go up and which ones will remain the same? So remember, it's all just the rotate operation. So you have to understand the rotate operation to understand what we're doing here. So anyways, just for the sake of brevity, I need to finish our example here because I have to still show you how to remove. So next, we have to do an RL rotation. I'm just going to do the second rotate operation. So when I do that, 17 is going to go up to the root of this tree. So in fact, the root actually gets updated here. So that means that 12 came down, right? There's this left subtree that goes along with this. Then I have my right subtree, because I'm dragging back up 30. And I should have 19 here and 40, just like in my picture over here. So I have 19 and 40. So these are heights are 0. This was 1. This is 2. We would make sure we update that. And we have 12 here. This should also be a 2. And of course, when I'm done doing this, of course, I update its height, which this one's 3. So notice here, I want you to take note of the fact that the height of the tree itself, it didn't change. It didn't go up. It stayed the same. My apologies. The turtle's just getting me very excited about these rotations. So notice that after this process, V is right here, right? Remember, that's the root of the subtree in this process. I recomputed its height. Now I'm at the root because I am the root. Because remember, when I did this rotate operation, when I promoted myself to be the parent, I need to make sure I update that I am the root. So that being said, this is the completion of the up process. So we're all done. And I'm also going to include one more example in the notes. If you want to see how you would insert 10 beyond this, I have another example in the notes. So just see the notes for one more example. So let's talk about removal. So first, actually, before that, are there any other questions about what we did in this example? Just before we proceed. So as long as you have an understanding of this up process, so just this process, the rebalanceAVL, where we walk back up the tree and we update their heights, but whenever we have an imbalance, we perform the appropriate rotation. As long as you remember, you see this process, removals are a piece of cake. Just there's sort of a caveat when it comes to removals. It's a little different than insertions. Insertions, notice that I just had to do one rebalancing operation. That's it. So if we're okay, let's head over here. Let's talk about removals. Because this is, we have to be a bit careful, okay? So I'm going to first just describe what we're going to do. I'm going to give you the pseudocode. And then we'll do an example or two. And I probably should bring us to the end of class after I talk about one small application of the AVL tree. Because there's some very interesting consequences that we get actually as a result for all of these operations. That I'm hoping, if you haven't realized it yet, I'm going to spell it out. So let's talk about removeAVL. Let's talk about this. So first you just apply remove of the BST. So you're going to first apply the remove that we talked about the other day. Then starting from the parent of the removed node, rebalance the tree. one thing I need to stress is that multiple rotations may be required to achieve this process that we talked about. The rebalanceAVL isn't going to just do one rebalancing. It may do several of them. Sorry, I'm just getting very excited about all of this. Several rebalancing operations may be required. So, let me just describe the pseudocode here. So let me just give you what the algorithm is. Algorithm, remove AVL. So imagine I give you some root. So wherever I'm starting this from, remember that in our remove function, we had it where you could potentially start it at a given node. I'm just preserving this, but you don't necessarily require it because you could just simply use remove from the BST, which has that functionality. So input has input and output. They're pretty darn straightforward. It's just root of the AVL tree and the key, and then just simply remove K from the tree. For the sake of brevity, I'm just going to give you what the algorithm itself is. So first I apply remove with the root and K. And then now we're just going to let V be the node where the removed node used to be. Now, you might ask, Dan, you just said it's supposed to be starting from the parent of the removed node. This is actually what rebalanceAVL is going to set up for you. So what will happen is you'll start off by updating the height at the removed node where it should be, and then it will immediately go to the parent, which is what I'm referring to up here. So rebalanceAVL sets up this whole process. So if you're wondering which node this is, I actually gave a specific name for it. So you remember how I had given names to nodes for my remove function? I had C, I had a C prime, I had a P and a P prime. What this is actually C prime. So this is, sorry, I'm getting very excited here. This is C prime in remove. So if you're wondering what this is, it's just simply C prime. So if, for example, you modified remove, what you could do is you could just simply have it where it returns C prime at the end of its process in case 1. So that's all you would have to do to achieve and get this node. So then after you got V, you're just going to do rebalance AVL on V. And I want to note that several rotations occur. So this is all the algorithm is for removals in an AVL tree. So all of it is pushed into two places, the remove that we talked about the other day and rebalanceAVL. So let's quickly do the time complexity analysis, and we'll have enough time to do an example and a quick just summary of what's going on here. So first, remove. We know how to do that in big O of log n because the height of the AVL tree is big O of log n. This node can be determined within remove if you need to. So I'm just going to extend this. And finally, rebalanceAVL we already established. This takes big O of log n. So that means that the time complexity, in the worst case, is big O of log n. So we can do insertions and removals in the AVL tree in big O of log n. Wonderful. So we're going to quickly head over here. I'm going to do an example with you because there's a couple of things I want to touch upon, but I'm going to quickly kind of go through an example with you because when I do a removal, it's a little bit more complicated. So we're going to see if we could hopefully get through this in time. Let's see. So I'm going to create a tree we're going to do removal from it. So I'm going to read it off level order for the sake of time. It's 30, 20, 55, 10, 25, 45, 60, a leaf, 15, a leaf, then we're going to have 40, 50, then we're going to have a leaf, then we're going to have 65, and then then the last couple levels, it should be just a leaf. To the left of 40 is 35. Then I have a leaf. Then I have just a whole bunch of leaves for everything else. Leaves all over the place. So what I'm going to do is I'm going to remove 20 first. So I'm going to perform a removal for 20. So I'm going to remove 20. So remember, I have this down process where I find where 20 is. Now I have a question for you. Do you remember those two cases I had for remove? So in this case, notice that both my children are internal nodes. So do I have case 1 or case 2? Case 2, very good. Very good. So remember in case 2, what I do is I go to my right and I find my successor. But notice I have no other ones than this one, right? So I'm going to copy over 25 into here. So this is going to be now 25, and I'm going to now delete this node. So now notice it's just case 1. So I have this node, P. It has 2 children. It doesn't matter which one. I know one is a leaf. The other one may not necessarily be a leaf. I'm going to remove these. And note that P prime is right here, by the way. I'm going to remove this, and I'm just going to place the leaf right there. So, you might ask, okay, so what's happening, Dan? Let me just make sure I accidentally erased the height there. So, now you might say, Dan, what's happening? So, notice here that I would start my computation of this at C, which is just a leaf node. Sorry, C prime. So, in this process, it's not an internal node, so I don't recompute its height. Then I go to my immediate parent, right here. And this is where the rebalancing is going to really start. So just to be clear, when you call a rebalanceAVL, it starts you at C prime. So you give it C prime as V, and then you go to the parent because you won't recompute the height here. But I must stress, there might be a node that is actually here that's an internal node. So just be very mindful of this. So now all I have to do now is go through the upward process from now we're going to just go our way up. And I'm just going to check this. Notice that I'm not starting at the smallest possible subtree where an imbalance occurs anymore. So that means that it's possible for several rotations to occur. In fact, what happens, if you ever were to dig into the juicy M word of this, what happens is when I don't have that property into play, what happens when I have a rebalance happen, the overall height of the tree might not change, but if I look at the parent of whatever would be the root, I might shift over the height in terms of its balancing by 1. So I might be passing the buck off to one other node somewhere else up the tree. meaning that there might be a case for more rotations. So anyway, so I remove that. Then what I do is notice that I have an imbalance that occurs at this node, the one with 25, right? There's 25 in it. So an imbalance happens here. I have V. I pick the taller of my two children. I have Y, and I have X. So I do an LR rotation. LR rotation. So I'm looking at the time here. Is it okay if I take 2 more minutes of your time? Is that okay with everybody? Because I don't want to take anybody's time this evening. Okay, I'm just going to finish this up. If you have to go somewhere, just watch the video afterwards. I'm just going to try to wrap this up and make one last point. Because it's not just one rotation we need here. So I'm going to do the LR rotation. So remember, that means I do rotate X twice because it's a double rotation. So I do rotate X, then I would rotate X again. So at the end of this process, you would end up with something that looks like this. So you would have 30, 15, 10, 25. Where this all looks pretty nice, right? This looks wonderful. So you would end up with something that looks like this. When you're done this process, this should look very nice to you because it looks a lot like my lovely picture I had before. So when I do this, you'll notice that the height of this one is nicely 1. And then I have 2 here because I would update its height appropriately. Because remember, I do rotate at X, but that's 15. So I'd update its height, then I move my way up. But let's take a look at what the rest of the tree actually looks like. So notice here that the right I have 55, I have 45, I have 60, I have 40, I have 50, and on the right I have 65. Just for the sake of time, I'm going to omit the leaf nodes. So I'm going to have 35 here. Notice that the height of this one is 1 because I have leaf nodes down here. I have 2, 1, 3. I have 1, 2, 4. So I have 4 versus 2. So if V's right here, because I've worked my way up here, I have V. I take the larger of my two children. Notice that I have an imbalance here because the heights differ by more than 1. So I have Y, and I'll have X again. So I'm going to perform an RL rotation. So I'm going to perform this rotation. And when I finish this process, remember, X is right here. So you know that's going to end up being the root of this entire tree when we're done this. So I do an RL rotation. The root will be 45. I have 30, 55, 15, 40, 50, 60, 50, 60, 10, 25, 35, and I'm just omitting the leaf nodes just for the sake of time. I suggest that you put them in after. Then I have 65 here. So I have 1, 2, 3, 1. Actually, I said I wasn't going to put in the leaf nodes, so I'm not going to do that. I know the height what this will be when I update this. It'll be 4, because this will be 3. Should be, sorry, let's see. Let's get a little, I don't want to get too ahead of myself. So let's see. Leaf nodes. So this is 1. This one's also 1. That's 2. This is 3. And this is 2, and that's 1. So yeah, we're okay now. So now that I'm at the root, it is the root now. I'm done, right? So one last remark I want to make quickly before we go for tonight, because this is the last thing I want to tell you about an AVL tree. So one last thing. So first thing you should notice is that this rebalanceAVL is wonderful because it's easy to adapt for insertions and removals, and it updates the heights nicely for us. But I want to talk briefly about an application for the AVL tree. Just very briefly. It's really nothing too fancy-pantsy, just to be very clear. But it is something that we haven't had yet in this course. So I need to address it. It's something very important for me to address. So let's talk about the AVL tree. Let's just talk about its performance. I want to quickly summarize this, just because I want to ensure you understand the significance of this. So all our dictionary, like put, get, and remove, and so on, like smallest, all of these can be implemented in big O of log n time in the worst case. So remember, that's in the worst case. It's not on average or anything, it's in the worst case. So the first one thing I should stress is the space usage. An AVL tree uses big O of n, where n is the number of records. It uses big O of n space. Now, I want to acknowledge two things quickly. The first one is that there also do exist other self-balancing trees. There are other self-balancing trees. So this isn't the only one in town. There is another one I want to mention. For example, we have the so-called red-black tree. It uses these rotation operations. So if you understand the rotations, red-black trees use rotations as well. So the red-black tree, some people call it an RB tree. So one thing I want to mention is that in practice, red-black trees are great for insertions and removals. But AVL trees are more rigidly balanced. Now, I must stress it's not a perfectly balanced binary search tree, right? But it's not bad at all, like I said. It's not that bad. But it is better than the red-black tree at it for being more balanced. So it's more rigidly balanced. I'll put that in air quotes. Sorry, I'm just getting so excited here. So it is more effective for access queries. So if you build the AVL tree and you just do a whole bunch of accessing or like get operations a lot, the AVL tree may have some benefits as opposed to the red-black tree, but you'll find that a lot of libraries that use tree-based data structures and underlying them, they oftentimes use red-black trees just because insertions and removals are presumed to be more important. But I want you to just be aware that both of these exist. One last thing, an application that I want you to notice is for sorting. So notice that with an AVL tree, you can perform all of your insertions into the AVL tree. If I do n insertions into the AVL tree, how long does that take in terms of big O? So I'll give you a heads up. It takes big O of n log n. So if I do n log n, so I do n insertions, I do n putAVL operations to build the tree. I consume big O of n space, by the way, when I do this, so it's not as nice as some of the other algorithms I've shown you. because you have to actually build the tree data structure. However, it is dynamic in the sense that you can add and remove records from it. So it's a dynamically resizable tree structure. You can do insertions and removals, and you can even sort. Can somebody tell me how I sort once I have the AVL tree? So I build the AVL tree. What do I do to it? So remember, there is a way I could go through the tree and ensure I get all of the information in sorted order. In-order traversal, exactly. So you just build the binary search tree, or build the AVL tree specifically here. You just do an in-order traversal, and there you go. That's how you can sort. So you get all of this dynamic data structure that you can insert, do removals, do all these other operations, plus you can sort with it in big O of n log n time if you're able to deal with the space. So anyways, with that being said, when we come back next time, we're going to start talking about generalizations of binary search trees, so-called multi-way search trees. So I say thank you very much, and I really appreciate the time you've given me. When we come back, multi-way search trees. So I'll say thank you very much, and have yourself a beautiful evening.